Welcome to this video on reaction schemes. Now in level 3 organic chemistry you learn so many different reactions. Reaction schemes is a way to bring together all of the reactions you've learned in organic both from level 2 and from level 3 into one type of question. So in this video there's actually no new information, but it brings together all of the previous information you might have come across. So let's quickly recap the reactions from level 2, the important ones we need to know. The first is addition reactions. And these happen from level 2 when we broke a double bond, and this is a fast reaction. So it started with an alkene, something with a double bond. And the key ones we learned were hydration, where you add an H2O, so this is where you break open the bond, one of the OHs adds on, one of the H's adds on, so you create an alcohol. Then you learned hydrogenation, where you add hydrogen on, so this turns an alkene with a double bond into an alkane, something that would have all H's around there. Then we learnt about halogenation, where you break open this double bond and add on a halogen, almost always Br or Cl. And finally we learnt about Markovnikov's rule, and this is where the rich get richer. So the important thing is there'll be a major and a minor product produced, for example when we add on a halogen. Now you're trying to decide which carbon the H will attach to. It's the one that already has the most H's. So if you're unsure on any of this, go back and watch the level 2 videos on addition reactions. Now also we learned about elimination reactions. Now this is going back from an alkane towards an alkene. So specifically we needed a reagent to make this happen, which was H2SO4 or sulfuric acid. And the examples were often an alcohol, something with an OH going back to an alkene, and that would have water produced, H2O, because you'd get the OH and the H joining together when you created this double bond. And you could get haloalkanes going back to alkenes. So instead of an OH, this might be a Cl or a Br. Now that would get kicked off along with another hydrogen, and that would create HBr or HCl. So these are the important reactions you need from level 2. And from level 3 we learnt some oxidation reduction reactions. The important ones were a primary alcohol going through to an aldehyde, then a carboxylic acid, and we used the oxidizing agents of acidified permanganate and acidified dichromate to make that happen. In the same way, they would oxidize a secondary alcohol. That would go through to a ketone, but then couldn't be oxidized anymore. When we learned about reduction, we learned that aldehydes could be reduced back to a primary alcohol, and would do this using sodium bromohydrate or NaBH4. Now the sodium bromohydrate would also reduce a ketone back to a secondary alcohol as well. And remember, if you're ever using these oxidizing agents, you're going to see a color change. Finally, in the second video, we learned about a whole bunch of reactions between acyl chlorides, esters, amides, and carboxylic acids. So you've got a list here of an acyl chloride which will go through to carboxylic acid or an ester, a primary amide or a secondary amide, and what you need to react this acyl chloride with. So you need to be familiar with all of these reactions because they could all come together in these exams. So now we're going to go through a typical question you might encounter in your exam. So this is something like propene can be reacted with water in the presence of acid to form a major product called A and a minor product called B. And then you're going to see a list of instructions and this big reaction scheme diagram. So you're starting with propene, which can be reacted with water in the presence of acid to produce a major product here, product A, and a minor product, product B. So this is going to be Markovnikov's rule. Then you'll go on with more instructions. So B is oxidized to form D, A is oxidized to form C, D reacts with SOCl2 to make E, E then reacts to create product F, D can react with G when you have alcohol and concentrated sulfuric acid, or it could make ester H when you mix it with alcohol A rather than alcohol B. So all of these steps are laid out and shown in this diagram, and your job is going to be to identify the reagents that happen if they're not listed and what all of these products A, B, C, D, E, F, G, and H are, as well as drawing the structural formula of these compounds. So you really need to understand all of the reactions to pull them together in a question like this. So we're going to go through this question so you can see how this would take place. So first of all, the important thing is you start with propene. So propene has 3 carbons and it has a double bond on there. Now the important thing is it goes to a major product, which is A, and a minor product. Now this is Markovnikov's rule where the rich get richer. And what it means is that when you add on a hydrogen, when you break open this double bond, the hydrogen is going to add on to the carbon which already has the most hydrogens attached because it's the richest. So here you'll notice that the carbon on the left has 2 hydrogens attached, the carbon on the right only has 1 hydrogen attached. Therefore the major product is when hydrogen attaches to this first carbon here. So this is an addition reaction where it opens up the double bond and that first carbon will get an extra hydrogen attached, so it becomes CH3 rather than CH2. The OH group from water will then get added onto this middle carbon here, so it'll be COH, and it'll still have one H attached to it because it's got this extra bond open to it. And then we still have this CH3 out on the right hand side here. So that's the major product where the rich get richer. Now that doesn't always happen. Sometimes you get the minor product as well, where the hydrogen actually attaches to the carbon with the least number of hydrogens. It doesn't happen as often, but it does still happen. So that would mean you'd break open this double bond where the carbon on the outside would get the OH group attached. Now, it doesn't happen often, but it does happen. So here we've got the carbon on the outside with the OH group attached. We've flipped it around. And you'll notice that this has two H's, so CH2 and the OH attached to it. And this middle carbon is CH2 as well. It's got its original hydrogen plus another hydrogen that's been added on from this open bond. And then there's still CH3 which comes off from down here. So this is an addition reaction where you need to follow Markovnikov's rule to get your major and minor products. Now that we've done that, we can look at what happens to both A and B. You notice that product A, which we've named as propan-2-ol, because it's propanol and the OH group is on 2, versus propan-1-ol, where the OH group is on carbon number 1. So they can undergo oxidation. If you want to oxidize here a secondary alcohol, you're going to get a different product if you try to oxidize a primary alcohol. So let's look at the oxidation reduction reactions we already know. So here we've got a primary alcohol gets oxidized to an aldehyde, then to a carboxylic acid, whereas a secondary alcohol gets oxidized to a ketone. So if we go back here and let's look at our secondary alcohol, our propan-2-ol. Now if we want to oxidize that, what's going to happen is you're going to kick off one of these hydrogens here and another hydrogen from the carbon, and you're going to get your double bonded oxygen creating a ketone. Now this can't be oxidized anymore. So product C as a ketone would be called propanone. Now if you're going to oxidize a primary alcohol, you'll get something different. So product D is where you get a carboxylic acid. Now you might ask, how do you know that it's not an aldehyde? The trick is, we've only learnt one reaction from an aldehyde. It gets oxidized onto a carboxylic acid. Whereas if you look at product D, you'll see that it goes on to create an ester, another product E, which is completely separate as well, under SOCl2. None of these are aldehydes being oxidized to carboxylic acids. So it must have got oxidized all the way through aldehyde, all the way to end up as a carboxylic acid for product D. And we draw that still with the CH3, CH2, but this final carbon has COOH because it has that double bonded O and the OH group as well. That's a carboxylic acid, and we'll call it propanoic acid. So this is great. We've got products A, B, C, and D. Now let's look at what happens to D going through to product E. And that occurs when we add in a halide, so SOCl2. So let's know if we start with a carboxylic acid, we add in SOCl2, that takes it to an acyl chloride. So therefore product E must be an acyl chloride. And we do that by replacing this OH from this carboxylic acid with a Cl to make acyl chloride. You'll notice there's still the double bonded O, which is from a carboxylic acid, and we can name this propanoyl chloride, again because it has 3 carbons, so we keep prop, and the ending for any acyl chloride is anoyl chloride. So this is great. Now we can take this propanoyl chloride and ask what would happen if we mixed it with ammonia. Now we can look at our reaction of when we take an acyl chloride, react it with ammonia, we can see we go to a primary amide. So this is great. Down product F must be a primary amide, and an amide is when the Cl group gets replaced with NH2. So we have the exact same structural formula, but instead of the Cl, we have NH2. And now that this is no longer an acyl chloride, instead it's an amide, we can rename it propanamide. So this is product F. So that's great. Now we can skip all the way back up to product D and see what might get us to ester G and ester H. So let's go through these one by one. So looking at D, our carboxylic acid, if we add alcohol B in the presence of concentrated H2SO4, we're going to go and get an ester. So let's look at what happens when we add an alcohol in the presence of H2SO4 to a carboxylic acid. It goes to an ester, which is perfect. So we know this is esterification. So coming back here, we have our original carboxylic acid, which is our C with the double bonded oxygen that comes from here, from this propanoic acid. And then we get this extra oxygen, which is bonded to alcohol B. And we know alcohol B is a primary alcohol, so it would link up to this first carbon over here and would have another 3 carbons. So carbon, carbon, carbon on this chain. So this would be called propyl propanoate. And you'll need to remember how to name your esters back from level 2. Now there's one other kind of ester we could form. Instead of reacting it with alcohol B, we could react it with alcohol A, which has a slightly different structure. Again, it would be in the presence of concentrated sulfuric acid. So if we look at that, remember our carboxylic acid is still going to go to an ester, still under the same conditions, but the specifics of where this oxygen connects up is going to be a little bit different because we're dealing with alcohol A here. So it's going to connect up to the CH, which has this OH attached to it here. So this left-hand side from the carboxylic acid is exactly the same. We've got our CH3, CH2 from here, C double bonded O, and then this O here will be connected to this O up here from the propan 2-ol. So it actually connects up then to the middle carbon in this chain because that's the middle carbon that has the OH group attached in a secondary alcohol. So we then have a different name. We've got this methyl group out the top, and then we've got ethyl propanoate. Now you don't need to get this name right to get the excellence marks, but this is how you would fully answer a question using this huge variety of different number of reactions we've learnt from organic chemistry to pull it all together in an excellence answer for reaction schemes.